Welcome to Keenon's training series courses for our partners. In this episode, I would like to provide you an introduction to some basic knowledge of service robots in order to give you a better understanding of service robot industry. This presentation will be divided into 6 parts. In the first part, I will introduce robot-related terms. In the second part, I will introduce robot-related sensors, and the following 4 parts are robot-related hardware, robot-related wireless technology, robot-related localization technology, and robot-related AI technology. Let's get started from the first part, robot-related terms. The first term is very basic, service robot. There are a variety of high-tech integrated advanced robots that provide necessary service for humans in an unstructured environment, mainly including household service robots, medical service robots, and public service robots. Among them, public service robots refer to robots that provide general service to humans in public places such as agriculture, finance, logistics, etc. As is known in those 3 figures below, the public service robots are divided into 3 categories, which are guiding robot, delivery robot, and intelligent security robot. As for Keenon Robotics, we are focusing on delivery robot. Keenon chose to enter the category field in the early stage because category has more complex scenarios, which can push Keenons to continuously solve problems in the process of commercial implementation, accumulate more data, and iterate software and hardware better. In the meantime, the market scale of category is large enough. The pain points are clear, and the industrial ecology is more dispersed, which is beneficial for Keenon to cooperate with merchants in a more market-oriented business model and excite the company's operating capabilities. Category merchants are highly sensitive to prices, which requires robotic products and service can actually reduce costs and increase efficiency. And the leading companies that come out of it are experienced companies with sufficient competitive barriers. The second term is RAS. It is a completely innovative robot applications model that began to emerge in the early 21st centuries with the development of machine vision and the proficiency of mechanical automation. It is especially suitable for small businesses that lack funds and manpower but want to increase efficiency. It is the most efficient business model for network applications. For more than 30 years, the robotics market has operated on the classic product design and scale business model. Under these scale strategies, new products are developed to meet market demands, then marketed and sold to the targeted customers as valuable assets. As a customer, he owns the equipment, depreciates the equipment as a fixed asset during its service life, and is responsible for the maintenance and repair of the equipment during the service life of the equipment. And at the end of product life, he is responsible for disposing of obsolete equipment. In a robotics as a service contract, the customer pays only for what is consumed, and all deployment, integration, support, and equipment maintenance costs are covered in a service level contract. As with any subscription business model, customers will get better prices by entering into long-term contracts with RAS providers. The next term is ROS, which is short for Robot Operation System. It is a software framework for creating robot applications. Its main purpose is to provide functions that can be used to create robot applications, and the created application can also be reused by other robots. ROS consists of a series of software tools, software libraries, and software packages that simplify robot software development. It is a complete open source project under the BSD license and can be used for research and commercial applications. Although ROS stands for Robot Operation System, it is not really an operation system. Instead, it is a Meta OS that can provide the functionalities of a real OS. ROS is a combination of pipeline, development tools, application capabilities, and the ecosystem. There are powerful development tools in ROS to debug and visualize robot data. ROS has built-in functionalities for robot applications such as robot navigation, localization, mapping, manipulation. They help in creating powerful robot applications. The designers of ROS know that the development languages used by each developer are different, so the development language of ROS are independent. Therefore, in addition to the official functions packages, ROS also aggregates a large number of open source function packages implemented by developers all over the world. For example, SlamTech released a ROS function package, RP Leader ROS, for its self-developed leader, RP Leader. Together with ROS, those open source function packages form a powerful open source ecological environment. The system structure design of ROS is also quite distinctive. The ROS runtime is composed of multiple loosely coupled processes. Each process ROS is called a node. All nodes can run on a processor or distributed on multiple processors. In actual use, this loosely coupled structural design allows developers to flexibly add various functional modules according to the functions required by the robot. The next term is delivery app, which is an application developed on Delivery Robot's Android system. Its primary interface connects users with delivery robots and enables seamlessly task assignment through various modes like delivery, multiple delivery, and cruise, alongside specialized functions including welcome and birthday modes. Additionally, the app empowers users to customize robot configurations such as moving speed, voice prompt, volume, background music, and more, ensuring a tailored and user-friendly experience. The left figure shows the Keenon delivery apps called Keenon Dinobot, and the right figure is the main menu of this app. Then I will introduce the next term, label. It is made of reflective material of different diameters. A usable label consists of 3 fixed points, 1 empty point at one corner, and any other endpoints. As you can see the left figure below, the label value is the sum of each point's value, whose value is shown in the right figure below. By reading the label value through the image module on the top of the label version robot, it communicates with the algorithm board and cooperates with the map to locate its position. The next term is mapping. It is a core part before a robot realizes autonomous working. For a robot, the process of describing the environment and understanding the environment mainly depends on the map in order to reach a certain destination, just like a human being. For Keenon robots, there are two ways to do the mapping: mapping with label and mapping with laser. For the former way, it relies on the image module on the robot's head to scan the labels pasted on the ceiling and record them into a mapping tool when a person pushes the robot around. For the latter way, it relies on the leader at the bottom of the robot to scan and generate a grid map, which is currently the most widely used map storage method for robots. It looks not much different from the map that people recognize and is essentially a bitmap image. But each pixel represents the possibility distributions for the presence of obstacles in the actual environment. As you can see the animations below, they show how those two mapping methods help the robot to localize itself. Scheduling relations is the last term I would like to introduce in this first chapter. It is also known as robot control system. By using AI scheduling algorithms based on deep learning, it realizes the optimal assignment of tasks, multiple robot path planning, and robot challenge management, so that the robot cluster can coordinate and work together without affecting each other and exert the greatest efficiency. Let's see the video below, showing multiple Keenon robot scheduling collaboration case. After introducing robot-related terms, let's move on to the next chapter, robot-related sensors. They are crucial hardware for the normal operation of a robot, like eyes of a human being. The first sensor is LiDAR, which is laser detection and ranging, also known as optical radar, which is a basic sensing technology in the field of autonomous driving. The working principle of LiDAR is the same as that of communication radar, which is time of flight. It explains that the emission medium uses infrared beams that are harmless to humans and animals instead of radio waves. A LiDAR system generally includes a laser emitting light source, a receiver, a servo motor, a bevel mirror, and an optical rotary encoder, as is shown in the left figure below. LiDAR determines the azimuth and distance of a target by measuring the time difference between the time a laser beam is emitted and the echo received by a rotating mechanical mirror. Since the laser radar actively emits laser light, it is less affected by changes in ambient light, and the distance measurement is accurate. In the right figure below, it represents the sample rate of T8's LiDAR, which is up to 8,000 and is the highest in the current economical LiDAR industry. The red rectangle shows where the LiDAR is in T8 robot. Followed by LiDAR. The next sensor I would like to introduce is ultrasonic radar. Although it is not applied in Keenon robots, but it is an extremely common sensor in service robot industry or even other industries. It has a more popular name, reversing radar. It is a safety auxiliary device when the car is parked or reversed. It can inform the driver of the surrounding obstacles by sound or a more intuitive display and help the driver eliminate the defects of blind spots and the blurred vision. The working principle of the ultrasonic radar is to measure the distance by the time difference between sending out ultrasonic waves through the ultrasonic transmitting device and receiving the sent ultrasonic waves through the receiver. Currently, there are three working frequencies of common probes: 40 kHz, 48 kHz, and 58 kHz. Generally speaking, the higher the frequency, the higher the sensitivity, but the smaller the detection angle in the horizontal and the vertical directions. So, a 40 kHz probe is generally used. Ultrasonic radar is waterproof and dustproof. Even if there's a small amount of mud and sand blocking it, it will not affect it. The detection range is between 0.1 to 3 meters and the accuracy is high, so it's very suitable for parking. However, since the working frequency belongs to the range of sound waves, the shortcomings of ultrasonic radar are also obvious, especially when the car is running at high speed. Due to the propagation delay of the ultrasonic signal, there will be a certain delay in the received information. In addition, ultrasonic devices also suffer from poor directionality, requiring more devices to cover the same area. Furthermore, weather conditions can greatly affect their direction effectiveness. The figure below shows a schematic diagram of ultrasonic radar. The next sensor is millimeter wave radar. It is a radar sensor that uses antennas to emit millimeter waves with a wavelength of 1 to 10 millimeter and a frequency of 24 to 300 GHz as radiated waves. Millimeter wave radar obtains physical environment information such as relative distance, relative speed, angle, and the direction of motion to the other objects by processing targeted reflection signals. The frequency band of millimeter wave is quite special, which is higher than that of radio, lower than that of visible and infrared light, so it's very suitable for the vehicle field. In addition, millimeter wave radar has become an indispensable part of advanced driver assistance systems by its absolute advantage of being able to penetrate dust, fog, rain, and snow, not being affected by bad weather, and the super capabilities that can work all weather and all time. The figures below show the basic working principle of millimeter wave radar and how it is applied to vehicles. The next sensor is binocular stereo vision, which is an important form of machine vision. It is based on the principle of parallax, uses image equipment to obtain two images of an object from different positions and calculates the position deviation between corresponding points of the image to obtain the three-dimensional geometric information of the object. Binocular still vision combines the images obtained by two eyes and observes the difference between them so that we can obtain a clear sense of depth, establish a correspondence between features, and correspond to the image points of the same physical points in different images. So this difference is called a disparity image. The schematic diagram of binocular stereo vision is shown in the left figure below. In the field of mobile robotics, depth perception is very important. Generally speaking, a monocular camera can also do some simple depth perception processing by acquiring a large number of data for learning and training. It can judge how far the object is based on prior knowledge, but the disadvantage is that it cannot enumerate every dataset. There will always be some objects that have not been learned and trained, so it is difficult to perceive. This is a congenital limitation of a monocular camera. The binocular is based on mathematical measurement methods. Just like our human eyes, we don't need to know what is in some place, but we can judge how far it is. Binocular still vision does not require a lot of prior learning, but it uses reliable physical information to analyze the scenes and obtain detailed information data. From the right figures below, it shows the location of binocular stereo vision sensor in the Keenon robot and what it sees with those sensors. The last sensor I would like to introduce is IMU, which is short for Inertial Measurement Unit. It is a sensor mainly used to detect and measure acceleration and rotational motion. Its principle is realized by the law of inertia. These sensors range from ultra-small MEMS sensors to laser gyroscopes with very high measurement accuracy. The most basic inertial sensors consist of 3 accelerometers and 3 gyroscopes. The gyroscopes are used to detect angular velocities in 3 directions, and the accelerometers are used to detect accelerations in 3 directions. The positioning information relative to the starting point is obtained by integrating the signals of the built-in accelerometer and the gyroscope, which is not affected by weather and other environmental conditions. Therefore, the independence of IMU makes it one of the key technologies in automatic driving. Now, let's go to Chapter 3, Robot-related hardware. They are very basic, but also very important. The first one is hub servo motor. It integrates the rotor, tire, stator, and the shaft. It is both a servo motor and a working wheel. There's no reducer, which directly eliminates the noise brought by the reducer. The name of the hub servo motor comes from the servo motor. The servo motor can control the speed and the position very accurately. It can convert the voltage signal into torque and speed to drive the control object. The hub servo motor has the same principle as the servo motor, both of which are permanent magnet synchronous motors. But the difference is that the servo motor is an inner rotor motor, while the hub servo motor is an outer rotor motor with a high precision encoder installed to make it large torque, large inertia, low noise, and high precision. It can directly install tires on the auto rotor to form a hub servo motor, which directly drives the wheels so as to replace the traditional servo motor plus reducer plus wheel solution. Hub servo motors are mainly used in various intelligent robots such as unmanned delivery robots, cleaning robots, disinfection robots, inspection robots, farming robots, robot motion chassis, AGV, etc. The figures below show the schematic diagram of hub servo motor and hub servo motor used in Keenon T5 robot, respectively. The next one is universal wheels. It is a so-called movable caster, and its structure allows horizontal 360-degree rotation. Casters are a general term, including movable casters and fixed casters. The fixed casters have no rotating structure and cannot be rotated horizontally, but can only be rotated vertically. These two types of casters are generally used together. For example, the structure of the Charlie is two fixed wheels on the front and two movable universal wheels near the push armrest on the back. As is shown below in the left figure, there are mainstream universal wheels with lock and without lock. There are many kinds of materials for making universal wheels. The most common materials are nylon, polyurethane, rubber, cast iron, and other materials. It is widely used in mining, mechanical equipment, electronic equipment, medical equipment, engineering, decoration, textile, printing and dyeing, furniture, logistics equipment, warehouse, turnover vehicles, chassis, cabinets, dust-free workshops, production lines, large supermarkets, etc. For Keenon robots, there are 4 universal wheels at the bottom, which are shown in the red rectangles in the right figure. The last one is integrated die casting. It is derived from the automotive manufacturing industry, which simplifies the traditional stamping and welding into a one-step process, referred to as the casting aluminum and the integration of body parts. This process is characterized by the manufacture of large aluminum parts through large tonnage die casting machine, mainly referred to the integrated process of auto body structure parts. The original design of a number of separate, scattered small parts are redesigned and highly integrated and then die casting machine for a module die casting into a complete large parts. As shown in the figures below, some Keenon robots are using integrated die casting chassis. Now, we are at chapter 4, robot-related wireless technology. In this chapter, I will introduce some key wireless technologies for service robot. The first one is 4G LTE. 4G is an abbreviation of the fourth generation communication system. In the definition of the ITU, any wireless data network system that reaches or exceeds 100 megabits per second can be called 4G. The full name of LTE is long-term evolution, a literal translation of long-range evolution. LTE is divided into 2 duplex modes, namely FDD-LTE and TDD-LTE. LTE significantly increases spectrum efficiency and data transfer rates. with peak rates of up to 50 megabits per second upstream and 100 megabits per second downstream. Compared with 3G era, the downlink peak of 10 megabits per second is 10 times faster. From the concept of the two, we can understand that 4G and LTE are not the same thing, but in general, LTE networks can meet the standards of 4G networks, and the 4G era is dominated by LTE networks, so the two are usually combined together, collectively referred to as 4G LTE. FDD LTE and TDD LTE are two different consistent modes of LTE. Most of the basic technologies of both are the same. The main difference is that FDD is a frequency division duplex, while TDD is time division duplex. The two are not compatible. FDD refers to the needs for two separate channels to transmit data. One channel to transmit information down, and the other channel to transmit information up. There is a protective frequency band between the two channels to prevent mutual interference between nearby transmitters and receivers. It is equivalent to a two-way highway, and the vehicles on both sides go their own way and complement each other. And the protected frequency band is like the middle of the highway. The transmitting and the receiving signals of TDD time division duplex are carried out in different time slots of the same frequency channel, and they are separated by a certain guaranteed time, can be compared to a wooden bridge. At the same time, only one side of people through, that is to say, the data upload and download are alternating in the same channel. The left figure below lists the frequency bands supported by Keenon W3 robots, and the red rectangle in the right figure shows the location of 4G module inside the Keenon W3 robot. The next one is Wi-Fi, which is a well-known wireless technology even in our daily life. It is a wireless LAN technology created in the IEEE 802.11 standard. Because of the close relationship between the two systems, Wi-Fi is often used as a synonym for the IEEE 802.11 standard. Since the release of the first generation of the IEEE 802.11 standards in 1997, the 802.11 standard has evolved through 6 versions. And before the release of Wi-Fi 6, the Wi-Fi standard was identified by the version number from 802.11b to 802.11ac. With the evolution of the Wi-Fi standard, the Wi-Fi Alliance has chosen to use a numeric serial number to rename Wi-Fi in order to make it easier for Wi-Fi users and device manufacturers to understand the Wi-Fi standard. Similar to traditional transistor radios, Wi-Fi networks transmit information over the air using radio waves, a type of electromagnetic radiation that has longer wavelengths in the electromagnetic spectrum than infrared light. Wi-Fi radiation waves typically have a frequency of 2.4 GHz or 5.8 GHz. These two Wi-Fi bands are then subdivided into multiple channels, each of which may be shared by many different networks simultaneously. When downloading a file over a Wi-Fi network, a device called a wireless router first receives the data from the internet over a broadband internet connection, and then converts it into radio waves. Next, the wireless router emits radio waves into the surrounding area and is captured and decoded by the wireless device that has initiated the download request. For Keenon robots, they all support 2.4 GHz Wi-Fi. The last one in this chapter is LoRa, which is short for long range radio. It is kind of long distance wireless transmission technology. It is based on spread spectrum technology and is a kind of LP1 communication technology. At present, LoRa mainly operates in the ISM frequency band, including 433, 868, 915 MHz, and so on. The technology was firstly adopted and promoted by Semtech company in the United States, with the aim of providing users with a wireless communication realizing long-range transmission and low power consumption. The LoRa network is mainly composed of four parts: terminal, gateway, server, and cloud. The biggest characteristics of LoRa are long transmission distance, low power consumption, and many networking nodes. LoRa technology integrates digital spread spectrum, digital signal processing, and forward error correction coding, which greatly improves the performance and changes the current situation in the field of embedded wireless communications. In March 2015, it launched the LoRa Alliance, an open, not-for-profit organization spearheaded by Semtech, which also includes activity of France, Octec of China, and KPN of the Netherlands. At present, the development member companies of the islands have reached more than 150 companies, including IBM, Cisco, Orange of France, and other leading companies in the industry. The first figure shows the advantages of LoRa: long operation range, long battery life, cheap, easy to deploy, and high data security. For a service robot, it is very important to know its own location so that it can provide corresponding services. Thus, in this chapter, I will introduce robot-related localization technology. Before I introduce leader slam, I will let you know what slam is. Slam means simultaneous localization and mapping, which is mainly used to solve the localization and map construction problem when the robot moves in an unknown environment. At present, the sensors used in SLAM are mainly divided into these two categories: LiDAR-based laser SLAM and vision-based VSLAM. Usually, the laser SLAM system calculates the relative moving distance and attitude change of the laser radar by matching and comparing the 2 point clouds at different times, and then completes the positioning of the robot itself. Radar ranging is more accurate. The error mode is simple, the operation is stable in the environment outside the direct light, and the processing of point clouds is also easier. At the same time, the point cloud information itself contains direct geometric relationships, making the path planning and navigation of the robot intuitive. Laser SLAM theoretical research is also relatively mature. Landing products are more abundant. The figures below shows how the laser SLAM used in Keenon robot to localize itself in the map. The other category of SLAM is VSLAM, which is short for Visual Simultaneous Localization and Mapping. It refers to the process of calculating the position and orientation of a camera with respect to its surroundings while simultaneously mapping the environment. It is a specific type of SLAM system that leverages 3D vision to perform location, and mapping functions. When neither the environment nor the location of the sensor is known, the process uses only visual inputs from the camera. Applications for visual SLAM include augmented reality, robotics, and autonomous driving. Unlike laser-based systems, which use laser beams to measure distance to walls and objects, VSLAM relies on information from a camera installed on the robot similar to the spatial perception of the environment by the human eye. With the help of this information, software constructs an always up-to-date 3-dimensional map of the room, within which a robot can determine its exact position and react to changing conditions. For Keenon new products such as T9 Pro, VSLAM technology is applied to help the robot localize itself in complex environment. Now we are at the last chapter, robot-related AI technology. In this chapter, I will introduce 2 AI technologies that are used in robots. The first one is image recognition. It refers to the technology of using computers to process, analyze, and understand images to identify targets and objects in various patterns. It is a practical application of deep learning algorithms. At this stage, image recognition technology is generally divided into face recognition and commodity recognition. Face recognition is mainly used in security inspection, identity verification, and mobile payment, while commodity recognition is mainly used in the process of commodity circulation, especially unmanned chefs, smart retail cabinets, etc. The figure below in the left are 2 popular use cases for image recognition technology: face recognition and license plate recognition. They are widely used in our daily life and make our life much more convenient. For Keenon T8 robot, the image recognition technology is applied to realize the plate detection feature. With this feature, our robot will know if the food has been taken out from the designated tray. The next AI technology I would like to introduce is speech recognition. Speech recognition takes speech as a research object. Through speech signal processing and pattern recognition, machines can automatically recognize and understand human spoken language. Speech recognition technology is a high technology that allows machines to convert voice signals into corresponding text or commands through the process of recognition and understanding. Speech recognition is a wide-ranging interdisciplinary subject, which is closely related to acoustic, phonetics, linguistics, information theory, pattern recognition theory, and neurobiology. From the videos below, you can see how the speech recognition is used in our robot and answer the customer's questions.
你好，哈森。
I am here.
How to find a beautiful girlfriend?
As an AI language model, I cannot guarantee or provide advice on finding a girlfriend. However, I can suggest focusing on building yourself as a person, being kind and respectful to others. Meeting new people through social events, online dating, or shared interests may help you find someone compatible with whom you can connect. But remember, it's important to keep an open mind and not have unrea.
你好，花生。
I am here.
Which hospital you will recommend in Canada?
Sorry, but as a language model, I have not been recommended any hospital or endorsed any medical institution in Canada or anywhere else in the world. However, Canada has numerous highly reputable hospitals, including Toronto General Hospital, Vancouver General Hospital, the Montreal General Hospital, and many others. If you are looking for recommendations for a specific medical condition, IW.
That's all for today's introduction for the basic knowledge of service robot, and thank you for your time. If you have any other questions, please contact Keenon Robotics for assistance.